Hey everybody, there's two things I want to go over in this video. The first is a little clarification on something that I said earlier. When we were talking about the particle model of thermal energy and we built a model for the heat, I said that the heat capacity of a substance is equal to its change in thermal energy divided by its change in temperature. This is not exactly correct. That was my mistake. The heat capacity of a substance is equal to the heat that goes into a substance divided by the change in temperature. Now you might say, why are these not the same thing? Well, in the context of solids and liquids, they absolutely are. As long as there's no phase change, any heat that you add to a solid or liquid will go into the thermal energy. But in gases, this is not necessarily true. And the reason has to do with the second topic of this video, work. We've studied work in this course already. We said that work happens when an object feels a force while it is moving from one place to another. But Patrick, you say, in the last video, you said that thermodynamics is all about the internal energy of gases, the thermal energy of gases. How can work come into play if it has to do with objects moving? Well, you're absolutely right. When it comes to gases, we really only care about their internal energies. But it turns out that it's possible for a gas to do work or for work to be done on it without the box or balloon or whatever the object is in actually moving from one place to another. An example I like to think about is a balloon. Imagine a balloon that's somewhat full and surrounded on all sides by air, just like a balloon in your everyday life would be. What happens if we try to make the balloon bigger? Well, you might say the balloon just has to get bigger, nothing very exciting. But there's more to it. In order to get bigger, the balloon must actually push the air around it out of the way. It has to literally make more space around it. Making more space like this actually requires some of the energy in the balloon. It's energy that has to be put into the surrounding air in order to push the particles out of the way. The way that we write this mathematically is like this. The work done by a gas as it expands or contracts is equal to the negative derivative of pressure as volume changes. This equation is not super illuminating, and we're not going to ask you to actually take integrals at any point in this course. But there's a much simpler version of this that comes out when pressure is constant. When pressure is constant, this equation just simplifies to work is just equal to negative pressure times the change in volume. A couple things to take away from this. First, if the gas cannot change its volume, then work will not be done. The example would be a box of gas where the box is a fixed size. If we add energy to the gas, it cannot expand because the box, well, can't change its size. And so no work will be done by the gas. But in the case of gas in a balloon, the gas can change its size because the balloon can change its size. As it expands or contracts, it will lose or gain energy in the form of work. Another thing to note about this equation is the fact that there's a negative sign in front. Well, what does that mean about the sign of work? Pressure is always a positive number, so it's not going to change anything here. But the change in volume might be positive or it might be negative. If the gas is expanding, getting bigger, then the change in volume will be positive and the work will be negative. On the other hand, if the gas gets smaller, then the change in volume will be negative and the two negative signs will cancel out and work will be positive. Why is this the case? Well, think back to what I said about why work is being done when the volume of a gas is changing. We imagined a balloon that was slowly getting larger. In order to get larger, it has to push the gas around it out of the way to make space for itself. Doing this requires it to use up some of its energy. It has to take some of its energy and give it to the gas particles around it to sort of knock them out of the way. And so when a gas expands, it's losing energy because that energy is actually going out into the surroundings. Now imagine a gas that's contracting instead. In this case, the exact opposite thing is happening. The particles outside of the container are pushing inwards on the gas, trying to make space for themselves. To do this, they have to give energy to the gas to kick the particles out of the way. This causes the gas to contract. So when a gas expands, it loses energy to its surroundings in the form of work. And when a gas contracts, it gains energy from its surroundings. When the gas is expanding, we say that the gas is doing work on its surroundings. And when the gas is contracting, we say that the surroundings are doing work on the gas. But as far as energy is concerned, this is just the difference between a plus or minus. Gas doing work on the surroundings means negative work because the energy from the gas is going into the surroundings. Whereas if the surroundings are doing work on the gas, then the work is positive because energy is going into the gas. Now we can hopefully start to see why I was wrong to say that heat capacity is the change in thermal energy divided by the change in temperature. Think about the energy conservation equation for thermodynamics. If work is zero, in other words, if the gas is not expanding or contracting, then the change in internal energy, which for a gas is just the change in thermal energy, will be exactly equal to the heat that goes in. In this case, the heat capacity of the gas will in fact be its change in thermal energy divided by its change in temperature. But if the gas is expanding or contracting, then we have a work piece in this equation. Work is not zero, and so we have to take it into account. If heat capacity is the heat that goes into the gas divided by the change in temperature, well, this is no longer equal to the change in thermal energy of the gas divided by the change in temperature. If you add energy to a gas and the gas expands, some of the energy that you added will go to increasing the temperature of the gas. But some of that energy will go to push particles out of the way to make room for the gas as it expands. And so the heat capacity will not be the same as if no work was being done. This way of thinking about processes in thermodynamics means there's actually two different versions of heat capacity when we're talking about a gas. Heat capacity, remember, is just the amount of heat you have to add to a substance to change its temperature by 1 degree. Heat capacity at constant volume just describes what this amount of energy is if the gas is not allowed to change its volume. Heat capacity at constant pressure, on the other hand, does allow the gas to change its volume. Because the gas is changing its volume, there is work being done, and the amount of heat that we have to add to warm the gas up by some temperature is going to be different. We'll study these more in detail in the next video. That's all for now. See you next time.